Hello students. Now in this video I will be continuing with the properties of Fourier series. In the last video we took the equations for Fourier series, and we also listed the properties of Fourier series for periodic signal, and in that we took the proof of linearity, time shift property, frequency shift property, and scaling property. So four of them has been completed. Now in this video we will continue with the remaining properties of Fourier series. Okay. Now after scaling, the next property is time differentiation. Okay. Now let's start with the definition of it. If x of t will provide x of k, then differentiation of x of t with respect to t. So if you take Fourier series of this, then it will be equal to j k omega naught into x of k. So here the statement is, if you have a signal x of t, then you perform Fourier series. So if you transform this, then you will get x of k. If you have a differentiation of x of t, then if you apply Fourier series, then we will get j k omega naught into x of k. So this is the statement of it. So let's take the proof. Okay. So in this case we'll start with the synthesis. So from the synthesis equation of Fourier series, so we have x of t is equal to summation k equals minus infinity to plus infinity x of k e power k j omega naught t. Okay. Now differentiating both sides with respect to t. So we are differentiating this both sides with respect to t. So that allows us to get x of t dt is equal to k equals minus infinity to plus infinity x of k e power j k omega naught t. Okay. So since we have to perform differentiation, this term x of k and the summation, so this becomes constant to that. So interchanging the order of summation and differentiation. So now if you interchange this order, so then what happens to this? Summation k is equal to minus infinity to plus infinity x of k d by dt e power j k omega naught t. Okay. Now if you differentiate this, so you will get j k omega naught into e power j k omega naught t. So this is what you are going to get if you differentiate this with respect to t. Now, if you rearrange this, k is equal to minus infinity to plus infinity j k omega naught x of k e power j k omega naught t. So here we are differentiating x of t with respect to t. Now here is the catch here. If you compare this expression, that is LHS, with the equation 1 here, so here you can observe this. Here, if x of t is transformed, you will get summation k varying from minus infinity to plus infinity x of k e power j k omega naught t. Now, if the differentiated version of this is transformed, so we will get what? So, if you observe below, we have the same limit, we have the same exponential here. This term is j k omega naught into x of k. So, that means if you compare this, the only difference here is the limit is same, this term is same, but j k omega naught x of k is the one which is going through synthesis here. So, that is why comparing this, the above equation with equation 1, we get d x of t by dt is equal to j k omega naught, or we can write precisely like the transformation of this will give j k omega naught into x of k. Okay. So, if x of t is transformed through Fourier series, we will get x of k. Then the differentiated version of x of t is transformed through Fourier series, then you will get j k omega naught into x of k. So, that is the meaning of this property here. Okay. So, let us move to the next one, convolution. Okay. So, there is a proof of this, and let us move to the convolution. So, it says if x of t is performed, integration, you will get x of k, y of t is transformed, we will get y of k. Then since this is convolution, then z of t is equal to x of t convolved with y of t. So, convolution in time domain is equal to in frequency domain, it is just simple multiplication, and that will be t into x of k into y of k. So, t into x of k into y of k, where t is the fundamental period here. So, let us take the proof of it. So, we will start with x of k. So, call this as 1, and y of k is 1 by t. So, we call this as 2. So, what about z of k? Z of k is 1 by t, z of t e power minus j k omega naught t dt. Substitute z of t here. Z of t is what? X of t convolved with y of t e power minus j k omega naught t dt. Now, this is the convolution. So, from convolution integral, so we can write the convolution of these two as integral of just for my convenience here, t is representing the limit. So, I will replace this with some other one. Select L will take that value, then this will be x of L y of t minus L dl. Okay. So, this is from convolution integral. Now, if you substitute that, so you will get integral of 1 by t is equal to t, L is equal to t, x of L y of t minus L dl. Okay. So, this is the term, and after this e power minus j k omega naught t dt. Okay. And let's interchange the order of integrals. Y means, so this is L and x of L is there, and here it is t. So, we have y of t minus L here. So, that means we can interchange the order for the convenience. So, 1 by t integral of L is equal to t x of L, and integral of t is equal to t y of t minus L e power minus j k omega naught t dl into dt. So, this t minus L I will replace with some other variable. Okay. So, put t minus L is equal to m. So, that transforms t is equal to m plus L, and dt will be equal to dm. So, let us do this. 1 by t, L is equal to t here, x of L, and this becomes t, that is replaced by m. So, m is equal to t y of m e power minus j k omega naught. So, this t is replaced by m plus L dl dm. So, 1 by t integral of x of L m is equal to t, that is one particular duration of this periodic signal, e power minus j k omega naught m e power minus j, we are splitting this, k omega naught L dl dm. Now, if we regroup this, 1 by t integral of L is equal to t x of L e power minus j k omega naught L dl into m is equal to t y of m e power minus j k omega naught m dm. From equation 1 and equation 2, so why I have considered this? So, observe here, this term x of k is equal to 1 by t integral of this term. Now, if you rearrange this, then we can write this as t into x of k is equal to integral of t x of t e power minus j k omega naught t dt, right. So, the same can be done for y of k as well. So, observe this, just cross multiply this here. So, you will remain with x of t e power minus j k omega naught t. So, this only this term can be written as t into x of k. Similarly, this term in equation 2 can be written as t into y of k. Now, using this, come to this one here, I am keeping this 1 of t as it is. You just take these two equations. So, this is x of L e power minus j k omega naught L dl. So that means this is very similar to equation 1, but we if we compare this to, in place of L we have T, here we have T, and here we have same things, and same happens to this as well. So that means this term can be written as T into x of k, and this term can be written as T into y of k. So from equation 1 and 2, so we can write this part as T into x of k and this part as T into y of k. So that's what I am going to do here. So taking this out, so I am rewriting this 1 by T into x of k and T into y of k. So that gives us T square by T into x of k into y of k. So this get cancelled. So here we started with z of k, that is equal to T into x of k into y of k. So this is the proof for convolution. Okay. So let's move to the next one, that is modulation property. So what does it say? If x of t gives x of k and y of t gives y of k, then z of t is equal to x of t into y of t. So this, when it is transformed into frequency domain using Fourier series, you will get x of k convolved with x of k. So this is the statement. So multiplication in time domain will be equal to the convolution of this in frequency domain. So that is what the modulation property states. So let's see, take the proof of it. So from, I'll directly start with z of k, z of t e power minus j k omega naught t dt. So this is 1 here. Okay. And let's simplify or substitute the value of z, that is x of t into y of t e power minus j k omega naught t dt. Instead of this, let's call this one as equation 1. Okay, so this will avoid some steps here. Now from synthesis equation of Fourier series, we have x of t is equal to summation. I am just changing this with some other variable, the limit x of L e power j L omega naught t. So you can call this 2 here. Now substituting equation 2 in equation 1, we get, so to get 1 by t integral of limit t, and if you substitute this, summation L is equal to minus infinity to plus infinity x of, I think I have used L here, so I have to write it here. I'm supposed to write L e power j k, so not k, L omega naught, okay, j L omega naught t into y of t e power minus j k omega naught t dt. So these two have a common base, so we can combine them, and coming to this, this x of L with respect to this integration will become constant. So we change the order, interchanging the order of summation and integration. So we are changing the order of summation and integration. So that provides this 1 by t into summation L is equal to minus infinity to plus infinity x of L. So integral of y of t, as it these two are common symbols, sorry, common base, we can combine them, e power minus j k omega. So I won't be using this k, I will write it in the last, e power j k j omega naught t into, so this one is having L and this one is k, this one is plus j and this one is minus j. Since I use minus j, so I will be writing k minus L, okay, dt. So now if I look back from frequency shift property of Fourier series, so from that I can write it like y of k minus L is equal to 1 by t integral of y of t e power minus j omega naught t into k minus L dt. So if I can go through the frequency shift property, so I can write it like this. Now based on using the same and this term here, this term along with this 1 by t, I can replace this term with y of k minus L. So which gives us, which leaves us summation L equals minus infinity to plus infinity x of L, I have to suppose using this in give a name here 3 in equation 3, and we started with z of k, I guess, equation 3 comma, we get z of k is equal to summation L equals minus infinity to plus infinity x of L y of k minus L. Okay, so from convolution sum definition, or just from convolution sum, we can write x of k convolved with y of k as L equals minus infinity to plus infinity. So x of k is constant and y of k is the time shifting one. So you can write it like this. So based on this, we can write therefore z of k can be written as x of k convolved with y of k. So hence the proof. Okay. So this is for the modulation property, and moving to the next one, that is Parseval's theorem. So the statement goes like this: if x of t is x of k, then so 1 by t integral of t modulation of mod of x of t square dt will be equal to summation k equals minus infinity to plus infinity x of k whole square. So this is the statement here. Now if you observe this LHS, So this is nothing but the average power of a periodic signal with fundamental period t. So I can write that the LHS in above equation is the average power of a periodic signal. So this is why we represent the power or average power of a periodic signal. So how we are going to represent that is P is equal to 1 by T. This will be from one particular duration, which can be represented like this: x of t whole square dt. Okay. So when the signal is in continuous time. So therefore, so we can write 1 by t So if you observe this, here in this Fourier series, we are dealing with complex sinusoids. Okay. Now complex sinusoids means we have to consider the complex signal as well as the real and imaginary part of the signal. So if the signals is complex, then we will represent it as the symmetric version, that is x star of t. So you can see this. The complex version of the signal, we represent it as x star of t. Now, which will be the imaginary part will just change their sign. So that's why we have taken the mod here, which represent that the signal can be real or it may be a complex valued signal. So we have to consider both of them. So this expression can be written in this way: 1 by t integral of x of t, okay, and the complex conjugate of this is x star of t dt. Okay, so we have to consider both of them, the complex conjugate of x of t and x of t as well. Now from synthesis equation of Fourier series, we have, so you can write, so what does it say? The synthesis equation, if x of t is equal to summation k equals minus infinity to plus infinity x of t. So this is just for clarification I am writing. It is not necessary that you have to write all of this k omega naught t. Okay, so this is the signal. Now if it takes the complex conjugate of this x star of t, then x star of t we can write k equals minus infinity to plus infinity x. Okay, I think I made a small mistake here. So I am supposed to write x of k, and here it will be x star of k e power minus j k omega naught t. So this is the major difference between this signal and this signal. If you take the complex conjugate, the sign of the imaginary part will be the opposite of it. Okay, so that's why. So using this in, I think we have not given a name here. Give it as equation 1. In this, in equation 1, so we have 1 by t integral of x of t summation k equals minus infinity to plus infinity x star of k e power minus j k omega naught t dt. So this one. So this thing we are replaced with this expression by the synthesis equation of Fourier series. So now let's interchange the order of integration and this summation. we have integration with respect to t here. So let's interchange that. So interchanging the order of summation and integration. So what we get, so I'll write the integral part here, sorry, summation part, k equals minus infinity to plus infinity x star of k into 1 by t integral of, so I'll remain with this x of t e power minus j k omega naught t dt. Now from the analysis equation, this part of the equation is nothing but x of k. So k is equal to minus infinity to plus infinity x star of k into x of k. Now these are the complex conjugate version of the signal. This is the transformation of x of k, x of t. Now we can take, if we take the magnitude of this, so we can write it like k is equal to minus infinity to plus infinity magnitude of x of k whole square. Okay, and now to the RHS, we have started from here, integral x of t whole square dt. Here you can see we started from here. I think this is equation 1, means let's go, yes, so here. So hence this proves the Parseval's theorem. Okay, and coming to the last one, there is no proof for this. I am just mentioned the symmetry property here. So the symmetry property, it says if x of t will give you x of k, then the first part says if x of t is real, then if you perform then if you take the complex conjugate of this, then complex conjugate of this in frequency domain will be x of minus k. So that is why here we represented the both x of k and x star of k. If you take the magnitude, it will be x of k whole square. So next, if x of t is real and even signal, then the Fourier series of this will be only the imaginary part, the imaginary part of this will be equal to 0 if x of t is real and odd sequence. Then if you perform Fourier series, then the real part of this x of k will be 0. So this is what the symmetry property says. So this completes the properties of Fourier series continuous time periodic signals. In the next video, we'll take some examples on the Fourier series, which might include the applying the properties as well. And this proof of this is very important of all the properties. So please go through this properties thoroughly. Okay, and I hope you have understood the derivation of all the properties. If you have any queries, do reply or comment in this video. Thank you.